Swinburne University of Technology.
Welcome back, everyone. In the first part of this week's lecture, we looked at using scatterplots to display the relationship between two metric variables. Now, from a scatterplot, it can be really hard to judge how strong a relationship is, so it's useful to have an objective measure of the strength. And for linear relationships, that's ones that have no curve in them, Pearson's R is a good objective measure of the strength of the relationship. Now, Pearson's R gives a measure of how closely the points in the scatterplot cluster around a straight line, and it takes values between +1 and -1. If there's no particular relationship, if there's just a general scatter of points in a scatterplot, then Pearson's R will be 0. If we had a perfect positive relationship, so all the points lying exactly along a straight line that slopes upwards from left to right, that's a Pearson's R of 1. Or if we had a perfect negative relationship, where all the points lie exactly on a straight line, but this one slopes downwards from left to right, then Pearson's R would take a value of -1. Now we have some rough guidelines for interpreting the values of Pearson's R. We say that if the value of the correlation coefficient is 0.75 or more, that's a strong relationship. If Pearson's R is between 0.45 and 0.74, we'd describe that as moderate strength. Between 0.25 and 0.44 we'd call weak, and a correlation less than 0.25 we'd refer to as being extremely weak. Now these are really rough guidelines, and you need to be very careful not to interpret weak as meaning unimportant. Whether a relationship is important or not depends very much on the context that you're working in. So if you were an engineer and you're trying to estimate the strength of a bridge based on the thickness of the steel that you used, then you'll want a really accurate prediction and a really strong relationship. But in the social sciences, on the other hand, even quite weak relationships might be of interest. And we'll talk a bit more about importance later on. Now there's a long, complex formula that you can use to calculate Pearson's correlation coefficient, but fortunately we can get SPSS to do all the hard work of calculation for us. So this is one of the scatterplots we looked at in part 1, showing the relationship between age and time spent playing outdoors. And together with that you'll see the output from the SPSS correlation procedure that shows us the correlation between age and time spent playing outdoors. And Appendix A9 in the textbook shows you how to produce that particular output. Now on the output I've circled the correlation for this particular example, and it's a correlation of 0.776. You'll notice that that correlation appears twice in the table, once in the top right-hand cell and once in the bottom left-hand cell. And that's just because the relationship between age and time is exactly the same as the relationship between time and age. Now a correlation of 0.776 is more than 0.75, so we describe that as a strong relationship. And if we were to give a brief description of the relationship in the sample, we'd say something like, in this sample of children aged between 4 and 12, there is a strong positive linear relationship between age and time spent playing outdoors. And then in brackets we'd give the value of Pearson's R, rounded to 2 decimal places, so R equals 0.78. And then we'd expand on that word positive by saying older children tend to spend more time playing outdoors. So rather than just saying the relationship is positive, it's more informative if we actually give that additional sentence saying that the older children tend to spend more time playing outdoors. Now I've been really careful here in how I've phrased that last sentence. I didn't say as children get older they tend to spend more time playing outdoors, because in this study we didn't watch what happened as children got older. It was a cross-sectional study. We just looked at a cross-section of children of different ages, and the older ones tended to spend more time outdoors. So that's how we phrase our conclusion here. That's how we phrase our description here. To look at another example, this scatterplot shows the relationship between age and flexibility in a sample of adults whose ages range from 18 to 84. You can see that Pearson's R is negative here. It's circled on the output. and this reflects the downward slope from left to right in the scatter plot. It's really important to include this negative sign when you're reporting Pearson's R. We could describe this sample relationship by saying something like, in this sample there is a moderate strength negative linear relationship between age and flexibility. We give Pearson's R equals minus 0.66, and then we say older people tend to be less flexible. So we're expanding on that word negative and explaining exactly what that means. Again, I haven't said as age increases flexibility decreases, or as people get older they become less flexible. In this cross-section of adults of different ages, the older ones tend to be less flexible, but that might be because of the nutrition levels they had as children, or maybe it was something to do with the type of exercise they were encouraged to do when they were young. So because we haven't actually observed what happens to people as they get older in this study, we can't say that as people age they become less flexible. So be really careful to avoid words like increase or decrease, or any other words that imply increasing and decreasing when you're describing the relationship from a cross-sectional study like this one. Now, as I said before, just because a relationship is weak, according to our rough guidelines, it doesn't necessarily mean that it's not important. Most of the relationships that you'll come across in the social sciences are weak, and they're still of interest to us. So a better way to get a feel for just how important a particular relationship is to look at the value of R squared. And R squared is also called the coefficient of determination, and what it tells us is what percentage of the variability in the dependent variable can be explained by the relationship. So suppose, for example, you were looking at the relationship between time spent exercising and blood pressure, and you wanted to know just how strong that relationship was. If I told you that that relationship explained 10% of the variation in blood pressure, that would be quite an interesting result, to be able to explain 10% of how much people's blood pressure varies. Hey, that's quite a lot. But if I told you it only explained 0.2% of the variation in blood pressure, then we'd say that the relationship was not particularly important. So looking at R squared gives you a good feel for just how important the relationship is in the context you're working in. So going back to the relationship between age and time spent playing outdoors, in that relationship Pearson's R was 0.78. So if we squared Pearson's R, that is, we multiply 0.78 by 0.78, we'd get a value of 0.61. Now that tells us that 61% of the variation in time spent playing outdoors can be explained by that linear relationship between age and time spent playing outdoors. So this is a really important relationship in estimating how much time children spend playing outdoors. Of course, it's also unrealistically strong in that the data was purely fictitious. So we wouldn't get a Pearson's R of 0.78 in a realistic study of this sort. Now there are some things that we need to be really careful about when we use Pearson's R to estimate the strength of a relationship. So have a look at this relationship between age and time spent playing outdoors. This is quite a strong relationship. Knowing a child's age would help us to predict how much time they spent outdoors. But if you look at the value of Pearson's R circled in the SPSS output, you can see that it's really, really small, 0.005. So this is telling us that there's practically no relationship between the two variables. Or to be a bit more precise, it's actually saying there's practically no linear relationship between the two variables. Pearson's R measures how well a straight line fits the relationship. So let's have a look at what straight line would best fit this relationship. Now you can see that there's a lot of scatter around that line, so it doesn't fit the relationship well at all. When the relationship is curved, Pearson's R badly underestimates the strength of the relationship. So let's have a look at another example. So here's another curved relationship. Now in this case, the straight line relationship captures some of what that relationship looks like. There is for most of the ages, a general downward trend, and that's being captured in this value of Pearson's R of minus 0.775. but it doesn't capture all of the relationship. So in fact, this value of Pearson's R would be underestimating how strong this relationship is. So the moral of the story here is that you should always check the scatterplot. If the scatterplot shows a curve in the relationship, then it's not appropriate to use Pearson's R to measure the strength. You'll be underestimating how strong the relationship is. There are also other things that we should be using the scatterplot to check for before we report Pearson's correlation coefficient. Have a look at this scatterplot and you'll see that most of the participants are aged between 18 and 25. And in between the ages of 18 and 25, there's not really much relationship between age and pulse rate. But there's an outlier. There's one person who's much older than all of the others, and this person happens to have a much higher pulse rate than all of the others. Now that outlier is acting as what we call a pivotal point. Without the outlier, we'd find practically no relationship between the two variables, but when we add this one unusual case, it gives us quite a large value for Pearson's R. And that's because we're fitting this straight line relationship, which is being unduly affected by that outlier. So this one case is actually determining the value of Pearson's R. If that particular person, that much older person, had had a very low pulse rate, we'd have said there was a negative relationship. And we wouldn't really want to base any conclusions on just one case, one pivotal case. So when there are outliers, we shouldn't be using Pearson's R. We should perhaps be removing the outlier and looking at the relationship for the remainder of the sample. There's one more situation in which Pearson's R is not a useful statistic, or where it can give us a misleading impression of the strength and even the direction of the relationship, and that's if there are subgroups in the data. So if you have a look at this particular data set, you can see quite clearly two separate clusters of points. There's one cluster in the top left-hand corner who tend to be younger and have higher pulse rates, and another cluster in the right-hand corner which tend to be older and have lower pulse rates. And if you fit a correlation coefficient to that, if you fit a straight line, you find quite a strong negative relationship. But if you looked at either of those two groups individually, you'd find that in each of the clusters there was practically no relationship between age and pulse rate. So not only should we be checking for curves and for outliers, but we also need to be checking for any subgroups, any obvious subgroups in the data. So again, always check the scatterplot before you start using Pearson's correlation coefficient. Now, what we've been talking about so far has all related to the sample. In one of our earlier examples, we found a correlation between age and flexibility in a sample of Australian adults. Now, we're interested here in more than just the sample. We don't want to know about the relationship in just that group of people that we happen to study. We want to be able to generalize our results to the population, to all Australian adults. And we're asking, is the correlation in the sample strong enough to convince us that there's also a correlation in the population? So for this we need a significance test, and we can use Pearson's correlation coefficient for this. So if you have a look at the output from the SPSS correlation procedure, you'll see that as well as showing Pearson's R in the output, it also shows the significance figure, or the p-value. In this case, 0.000. So this value is less than 0.050, so the sample relationship is statistically significant. We can conclude that there is a relationship between age and flexibility in the population. When we quote the statistics to support this conclusion, we give the value of Pearson's R, the size of the sample, and the p-value. So all three statistics are required. And these three figures should all come from the same box in the output table. So in this case, the p-value is less than 0.050, the sample relationship is significant, and to support that, we need to quote R is minus 0.66, so that's the correlation coefficient rounded to 2 decimal places. The sample size is 247, and the p-value is reported as p less than 0.001. If you look closely, you'll see that there are different values for sample size, for n, throughout this table. There's a 249, a 247, and 248. So why is this? Why have we got different sample sizes here? Well, it's because some people told us their age, but we didn't have a flexibility score for them. Others we had a flexibility score but no age, and some people we had neither their age nor their flexibility. So we knew the age of 249 people. You can see that the value of n in the age in years cell, that top left-hand corner cell, is 249. In the bottom right-hand corner, n is 248. So we knew the flexibility for 248 people. But when you look at the cells that include both flexibility and age, there were only 247 people for whom we knew both their age and their flexibility. And it's those 247 people that we used in the calculation of Pearson's R. So that's why we choose that particular sample size when we report Pearson's R. So once again, those three figures that we're quoting to support our conclusion, all three figures come from the same cell in the output. So the significance test itself tells us we're convinced that there's a relationship between age and flexibility. But we'd like to go a little bit further than that. We'd like to be able to say something about how strong the correlation is in the population. And this is where the 95% confidence interval comes in. So in our sample of 247 adults, the correlation between age and flexibility was minus 0.66. And if we have to make a guess, then we would guess that that would be about the correlation in the population as well. But with a 95% confidence interval, we can go a little bit further. Looking at the confidence interval calculator that you'll find on the website, the 95% confidence interval is between minus 0.72 and minus 0.58. So that tells us we're 95% confident that the correlation in the population is somewhere between minus 0.72 and minus 0.58. Now you'll notice when we write that formally, we use the Greek symbol rho to present the strength of the correlation in the population. So rho, R-H-O, is not an italicized P, it's a Greek symbol. Now there's one final thing that we need to be aware of when we're interpreting correlations. Just because two variables are correlated with each other doesn't mean that there's a causal relationship. It doesn't necessarily tell us that one variable is causing the changes in the other. Sometimes people find it difficult to recognize when a conclusion is causal, so we're going to look at a few examples. There was a study on American teenagers a few years ago where the researchers recorded the amount of time spent watching TV and their grade point average, which is essentially a measure of how well they were doing in school. They found a negative correlation between time spent watching television and grade point average. Now this study was observational, so we can't draw causal conclusions here. We can't say that it's the large amount of time spent watching TV which is causing some of the teenagers to get poor marks in school. So what can we conclude from the study? We could conclude that the teenagers who spend more time watching television tend to have lower grade point averages. That's a valid conclusion. It doesn't imply any cause or effect relationship. We're not saying why they get lower grades in school, we're just saying that teenagers who watch more television do get lower grades in school. So let's explore a little bit about why teenagers who watch more TV might get lower marks. Maybe it's the time spent watching TV which is resulting in the lower grades. Maybe there is a causal relationship. Perhaps teenagers who spend more time watching TV don't have any time left over for study, and so they don't do very well in school. On the other hand, maybe both the low grades and the time spent watching television are related to a confounding factor, say disengagement. Perhaps teenagers who are more disengaged from life in general tend to watch more TV and also tend to do poorly in school. So let's have a look at a few conclusions that might have been made from this study and look to see whether they're causal or not. So each of these first ones here imply a cause and effect relationship. The amount of TV that teenagers watch has an effect on their grades. Now that's fairly obviously causal because we're talking about the effect that the amount of television has on the teenagers' grades. The second one, watching more TV makes teenagers get lower grades in school, again, is a fairly obvious causal conclusion. But the third one people tend to miss as being a causal conclusion, but it is also implying a cause and effect relationship. Parents should restrict the amount of time their teenagers spend watching TV so that they will do better in school. Now, that recommendation suggests that it's the amount of time spent watching television which is going to affect the grades in school. It's a causal conclusion. This is actually one of the recommendations made in the original study, but it's a really flawed recommendation. If we think about why time spent watching television and grade point average might be related to each other, one of our explanations was perhaps they both reflect the level of disengagement of the teenagers, that there's a confounding factor going on here. If that's true, and we force the teenagers to watch less television, we remove the television from the house, that's not going to make them any more engaged, and so it's not going to improve their results in school at all. So this is an example where the researchers have made a conclusion which is not valid for an observational study. Let's look at one more example. Suppose we conducted a study of businesses where we recorded the number of managers in the business and the amount of money lost to fraud over the past 5 years. And we found a positive correlation between the number of managers and the amount of fraud. Businesses with more managers tended to have lost more money. So can we conclude that the managers are causing the fraud? Or should we recommend that businesses should reduce the number of managers as a way of reducing fraud? Well, no, because both of these conclusions imply a cause and effect relationship. But this was an observational study. The researchers didn't manipulate the number of managers in each business, they just observed how many managers there were. There's a really important nuisance variable here, which is acting as a confounding factor, and that's the size of the business. So while we have concluded that businesses with more managers tend to have more fraud, the study is observational, so we can't draw a causal conclusion. The confounding factor here is the size of the business. You would expect that larger businesses would lose more money to fraud, and you would also expect that larger businesses would have more managers. So here it's probably the size of the business which is having the direct impact on the amount of fraud. We can never draw causal conclusions from observational studies, and we always need to be aware of that when we're reporting on correlations. So what should you be doing this week? You should read through topics 7.1 to 7.5 in the text and complete the exercises in those sections, and then complete topic test 7.
This has been a Swinburne production.